So this lecture is going to continue our investigation into solving systems of linear equations. So just as a reminder, in our previous lecture, we saw that if we have a system of linear equations, and the important thing here is that they must be linear, then there are three possible solution sets. We can have a solution set that has exactly one solution, we can have a solution set that has infinitely many solutions, and finally we can have a solution set that is empty, so the system doesn't have a single solution. Now, up until now, you've probably been using fairly ad hoc methods for solving simultaneous equations, but the goal of this part of the course is to develop a routinized technique for finding the solution set. So we're going to start with a definition. We're going to say that two systems of linear equations are equivalent if their solution sets are equal. Now, it's important that we know that we use equivalent and not equal, because equivalent is kind of a weaker form of equality. What do I mean? So if we have a look at this first system over here, and we plot the graphs, we're working with two variables, and we've got two equations. And over here, I've plotted the graph of y minus is equal to minus x, and over here we've got the graph of y is equal to x. So I've just slightly rewritten the two equations. And as you can see, our solution set is a single point 0, 0. If we have a look at the second system over here, now I've got three equations, also in two unknowns, and plotting those three graphs, I get this picture over here. And again, you'll notice that the solution set, so the point which solves all three equations at the same time, is again 0, 0, which is our solution set for these. And so by this definition we've got up here, these two systems are equivalent because their solution sets are equal. So this is quite an important thing to realize, because sometimes we might have a very complicated system which we want to solve, and if we can transform it into a simpler system with the same solution set, that will help us a lot finding the solution. So how can we go about transforming our systems of linear equations? Well, we've got three operations that we can use to transform a system into a different one, and it's actually going to turn out that if we use these three, it's going to be a transformation into an equivalent system. So let's have a look at what our options are. The first one that we have is that we can swap the locations of two equations in the list of equations. So if we go back to our previous example and have a look at these three equations, it makes sense that if we swap, for example, the first two equations, so we end up with 4x plus 3y equals 0, and 2x minus y is equal to 0, and minus x plus 2y is equal to 0. Well, that shouldn't change our solution system. It would be the same as plotting the graphs in a slightly different order. So it makes sense that we get an equivalent system if we swap two rows. Now let's have a look at the second thing that we can do. We can multiply each term in an equation by a non-zero quantity. So I'm just going to mark here that these two systems are equivalent. Again, if we have a look, now imagine that I times my second equation by minus 2. So I didn't do anything to my first equation. I times my second one by minus 2, so I get minus 8x minus 6y equals 0, and I didn't do anything to my third one. Well, in this case, this graph over here is going to be exactly the same graph that it would have been before. So we haven't really changed anything by multiplying a single equation by some constant multiple. The final thing that we can do, which sounds a little bit more tricky, is we can multiply each term of one equation by some quantity, so we already know we can do that, and add these terms to a second equation on both sides of the equality. And we leave the first equation the same, but replace the second equation with the new one. So what's this saying? This is saying that I can, for example, multiply, so I'm going to work with these two rows. So let's just get a copy of this. Oops. So suppose I'm going to work with these two rows. What this is saying is that I can leave my first equation the same. My second equation, I'm going to say, so I'm going to call this equation 2 minus, let's say, 2 times equation 1. So that's going to give me equation 2, 4x minus 3y, minus, and I want 2 times equation 1, so that's going to give me 4x minus 2y. And then I need to do the same thing on the other side. Now in this case it doesn't really appear that we're doing anything. I'd have the 0 from my second equation, and I'm subtracting off 2 times the 0 from the first equation. And if we have a look at what this equation becomes, it becomes, so I'm looking particularly at the left-hand side here, I've got a 4x minus 4x, so my x's go away, and I've got a minus 3y plus 2y, so I've got minus 3 plus 2y, so I've got just y is equal to 0. And this here is an example of why it can be very useful to use these terms, because looking at the equations in their original form over here, it wasn't clear what our solution could be. But by simply using this technique, we have in fact found an equation that tells us that our y has to be equal to 0. And just to finish off here, I would have left my last equation the same. So we've transformed this set of equations into a slightly simpler one that looks like this. And by doing so, we've already found one coordinate for our solution. And then we could just plug that in and find out the x value. If you want to think about why it is the case that this third step is valid, notice we know that multiplying each term of one equation by some quantity doesn't change it. And remember, we have an equality, so if I add both sides of one equation to another equation, I'm just adding the same thing on both sides. And we know that it's fine to just add a constant so long as you do it on both sides. So there's no reason why we can't also add something with variables in, because the x and the y are the same in both equations. So the theorem that we have says that the equations that we've just talked about, equation operations, preserve solution sets. And writing it out formally as a theorem, if we apply one of the three equation operations that we just saw to a system of linear equations, then the original system and the transformed systems are equivalent. So remember we said that the two systems will then have the same solution set. So this is very useful. It gives us a way of transforming some possibly quite complicated linear system into something that's much easier. And that is essentially what we're developing a routine for. You're welcome to go and have a look at the proof. You don't need to learn it, but it is quite interesting. However, we're not going to cover it in this lecture. So let's see how we can use these ways of transforming equations to help us solve, for example, this problem. So just to have a check, notice that we have 3 equations and 3 unknowns. And you could certainly solve this by maybe solving the first one for x1 in terms of x2 and 3, and then substituting it in and on, but this can get tedious fast, so we want to develop a quick method to do this. So the first thing that I'm going to do is note that it was very useful in our example over here when I subtracted a version of row 1 from row 2, because it meant I eliminated the variable x. So we're going to use a similar idea over here. What I'm going to try and do is find an action that I can take that is going to eliminate x1 from the second row. And then I'm also going to do the same thing and try and eliminate 2x1 from the third equation. So it might not be clear why I'm doing it in this particular order, but as we develop the technique, you'll see. Okay, so here we go. I'm going to focus on getting rid of this x1 first. Well, if I have a look, if I just subtract row 1 from row 2, then I will have eliminated that x1. So what I'm going to do from here is say row 2 minus row 1. So I'm leaving row 1 as it was. I'm not changing it. But I'm subtracting row 1 from row 2. So I'm saying x1 plus 3x2 plus 3x3 minus, this is the row 1, is equal to, and then I've got my row 2 minus row 1. And if I just complete this, I'm going to have x1 minus x1, so we're going to have 0x1, 3x2 minus 2x2 is going to give me an x2, and I've got a 3x3 minus 2x3, which is going to give me just x3. And I've got 5 minus 4, which is just 1. So I have transformed this second equation into the equivalent equation, which just says x2 plus x3 equals 1. And my third equation stays the same. So these 3 are the new equivalent system of equations that we're working with. So I want to play the same trick now, and I want to get rid of this 2x1 here. And again, I'm going to use row 1. So what I'm going to do is I'm going to write down, I'm not going to change my first equation. I'm not going to change my second equation. But what I am going to do is, to get my third row, I'm going to say row 3 minus, well, I want to get rid of 2x1, so I'm going to have 2 times row 1. So that's going to give me 2x1 minus 2x1, so that's 0x1, got a 6x2 minus 4x2, so that's going to give me 2x2, and then I've got a 5x3 minus 4x3, so that's going to give me 1x3, and then I've got a 6 minus 8, so that's going to be a minus 2. So now we have a third set of equations which is equivalent to the first one. What next? Well, the next thing I'm going to try and do is I'm going to try and get rid of this term. So notice, if I subtract 2 times row 2 from row 3, then I will get rid of this 2x2 term. So let's go ahead and do that. So I'm not changing my first row. I'm not changing my second row. But what I am saying here is row 3 minus 2 times row 1. So I've got a 0x1 from the third row, subtracting 2 times 0, which is still 0, so that keeps my 0. Now I've got 2x2 minus twice x2, so that gets rid of that x2. And now I've got 1 times x3 minus 2x3, so that's going to be a minus x3. I've got a minus 2 minus 2, which is going to give me minus 4. So having a look at what we've got, I'm going to do one more little step. I'm going to multiply this third equation through by minus 1. So my new system is going to be unchanged top row. I'm going to simplify as much as I can. So I'm leaving out the 0 times x1 in the second equation, and I'm multiplying our third row by minus 1, in which case I get x3 is equal to minus 4. So this set of linear equations is equivalent, so it has the same solution as our original set up here. But notice that with the work that we've done, we can now actually read off the solution very easily, because our third equation tells us exactly what x3 has to be equal to. We know that we have to have x3 is equal to minus 4, and now we can plug that minus 4 into the x3 in our second equation, which will tell us that we have to have that x2 minus 4 is equal to 1, so straight off we know that x2 is equal to 5. And now that we've got x2 and x3, we can plug those values into our first equation so that we can solve for x1. So we get x1 is equal to, I'm taking these two over to the other side just to help, so I've got minus 2 times x2, so minus 10, minus 2 times x3, so that's going to be plus 8, and then we've got plus 4, so we can finally find our solution is just x1 is equal to 2. So the transformations that we've made have enabled us to find a system from which we can easily read off the solutions. And in fact, the technique that we're going to develop takes this process a little bit further so that we can read off solutions even quicker. But this was just to demonstrate that by using the 3 equation transforming options that we have, we can transform a system which we can't read the solution of into a solution from which we can read the solution. So let's have a look at a second example. So just to go back briefly to this example, notice that in this case we have a unique solution. So in our second example that we're going to have a look at, we're going to play exactly the same game. We're going to use the same tricks. We're going to aim to get rid of these 3 terms here. And in fact, we're going to go a little bit further. But let's start off. So we're going to leave our first equation as it is. We're going to take our second equation and we're going to subtract our first equation from it. So we're going to say our second row becomes row 2 minus row 1. So we've got an x1 minus x1, which is 0. We've got an x2 minus 2x2, so that gives us a minus x2. We've got an x3 minus 0 to x3, so that's just going to stay as an x3. And we've got a minus x4 minus x4, so that's a minus 2x4. And then we've got a 3 minus 7, so that's minus 4. And we're not doing anything to our third equation. Next up, we want to get rid of this 3x1, and really the only option we have is to subtract 3 times row 1. So we're not going to do anything with our first row. We're not going to do anything with our second row. But what we are going to do is we're going to take our third equation and say row 3 minus 3 times row 1. So that's going to give me a 0 and a minus 5x2 plus 5x3 minus 10x4, and that's going to be equal to minus 20. So you can check my working, but I think that's right. Okay, the next thing that we want to do is we want to get rid of this 5. So we don't want to end up reinserting an x1, which would happen if we added or subtracted a multiple of row 1. So we're just going to work with row 2. So what we're going to say is we're not changing row 2. And now we're going to say row 3. Well, we need to say minus 5 times x2. And that's going to give us 0x1 plus 0x2 plus 0x3 plus 0x4 equals 0. Okay, so what should we do next? Well, let's notice a couple of things. Firstly, if we look at the third equation over here, this is really just saying 0 is equal to 0, and that is always true. So in fact, it's only the first and second two equations that are things that we really need to work with, because whatever we do, 0 will always be equal to 0. So if we look a little bit more at our first and second equations, in particular the second equation doesn't depend on x1, it depends on x2, x3 and x4. On the other hand, our first equation depends on x1 and x2 and x4. Now it's going to turn out to be handy if we can have our first equation depending on x1 and also x3 and x4. So if we can somehow get rid of this x2. And I'm not giving you a full reason for that right now. I'm just going to say it'll be handy. And when we come to actually writing down the technique, you'll see why. Okay, so what I want to do is I want to get rid of this 2x2. Well, the only thing I can really do is use my second row. So what I'm going to do is I'm going to say my first row is going to be replaced with, well, I'm going to say my first row becomes my first row plus 2 times my second row. So what does that give me? That gives me x1 plus 0x2 plus 2x3. And what happens here? We've got an x4 minus 4x4, so that's a minus 3x4. And that's going to be equal to 7 minus 8, so that's minus 1. My second equation, I'm going to write this out as x minus x2 plus x3 minus 2x4 is equal to minus 4. And just to make life a little bit easier, I'm actually going to imagine that I've multiplied my second equation by minus 1. So my signs change. I'm going to have minus there, and a plus there, and a plus there. So notice what's happened. We've gone from an equation, a system of equations with 4 unknowns and 3 equations, to 4 unknowns and 2 equations. And I'm pretty sure that you remember that from school or from an earlier maths course, if you want to solve for 4 variables, you need 4 equations. So what can we do here? Well, again, let's have a look at these 2 equations. If we have a look at the second equation, notice that there are many, many values of x3 and x4. In fact, any values we pick for x3 and x4 will give us a way to calculate x2. So x3 and x4 are free variables. I could have similarly said, well, I could pick any value for x2 and x3 and then work out x4, but we just tend to work from the lowest upwards. So I'm going to declare that my x3 and x4 are what we call free variables. They are things which can take on any value, so they're free. So I'm going to let x3 be equal to a, where a is any number in real numbers, and I'm going to let x4 be equal to b, where b is any number in real numbers. And then notice we can also in fact write x1 in terms of a and b. So with this we have x1 plus 2a minus 3b is equal to minus 1, and x2 minus a plus 2b is equal to 4. So notice what happens. We can pick any value for a and any value for b, and that will dictate to us the value of x1 and the value of x2. So this is a case where we have infinitely many solutions, because for any pair of numbers we choose for a and b, we get a different solution for x1 and x2. And this is going to be the characteristic look of any solution space that has infinitely many solutions. So we don't get a neat cut and dried single answer like we did for 3 equations, 3 unknowns. So here we had x1 equals 2, x2 equals 3, x2 equals 5, and x3 equals minus 4. That was a unique solution. But here, in this case, we have infinitely many solutions depending on what values we pick for a and b. So if you remember from the previous lecture, we actually saw 2 different solutions for this particular system. We saw that x1 equals minus 2, x2 equals 4, x3 equals 2, and x4 equals 1 is a solution. So what we've really done to find that solution was we said a is equal to 2 and b is equal to 1. And then if you plug those values for a and b into our 2 equations here, you get x1 is equal to minus 2 and x2 is equal to 4. On the other hand, if you were instead to pick that a is equal to 1 and b is equal to minus 3, then you end up with x1 equals minus 12 and x2 is equal to 11. And so for any particular values of a and b that you pick, you get different values for x1 and x2. So how can we go about writing the entire solution set? Well, we're going to need some set notation. First of all, let's write x1 and x2 in terms of a and b. So I'm going to say x1 is equal to minus 1 minus 2a plus 3b. We know that x2 is equal to 4 plus a minus 2b. And just so that we have the full set, we have x3 is equal to a and x4 is equal to b. So what this means is that any point in the solution set has to look like minus 1 minus 2a plus 3b for the first component, 4 plus a minus 2b for the second component, a for the third, and b for the fourth. And then when you pick a particular value of a and b, that will give you the point. So if we want to write our solution set, we want it to be the set of all points of this form. So let's just copy that straight over. So we want all the points of this form where we have a and b drawn from real numbers. So this is our infinite solution set. So let's look at one final example. This is a simple case of two variables and two equations. And we're going to use the same technique as we have before. So what we want to do is add some multiple of the first row so that we can get rid of this minus 3x1 term. So we're changing the second row, not the first, so we'll write down the first row. And what we need to do is we need to say, well, I'm going to take my second row and add half of the first row in order to get rid of that 3x1. So I've got minus 3x1 plus 3x1, so that gives me 0x1. Then I've got x2 minus, well, this is just going to be minus x, which gives me 0. And then I've got 5 minus 4, which is 1. And immediately here you should start being a little suspicious, because if we rewrite our second equation, what we end up with is 0 is equal to 1. Now in the previous example we had 0 is equal to 0, which is always true. On the other hand, 0 being equal to 1 is never true. There are no values of x1 and x2 that I can pick which will make 0 equal to 1. So this is a case where we don't have a solution. And in fact, if you were to plot these two lines in GeoGebra or something like that, you would find that this is a case where we have parallel lines, they never intersect. And so it would be very strange if we had found values of x1 and x2 which made this system of equations work. So the point of this lecture has been to show you a slightly different method than you might be used to for solving systems of linear equations. But I'm pretty sure that you got quite bored watching all the manipulation and probably got frustrated because if you were following along, I was writing x1, x2, x3, x4 so many times, so many steps. So what we're going to talk about in the next lecture is a way to speed up this process. Still using the same ideas of transforming a system into an equivalent system that's easier to read solutions from, but it's going to be a lot speedier.